So today we're going to talk about energy transformations and how energy changes forms. Energy is required to do work, and in science we talk about doing work. Work is done when we use a force to move an object a distance, and we'll use fuels and other sources of energy in order to accomplish work or do tasks that we want to do. There is a law of conservation of energy. The total amount of energy on Earth stays the same. It can either be created or destroyed. It can only be converted from one form to another. This is within the energy transformations that we're looking at when we're converting from, say, using a battery to cause a electronic device to turn, or when we're burning wood in order to produce fire from heat energy. That is what we're talking about with the law of conservation of energy. And Albert Einstein, he came up with E equals mc squared, showed that if we destroy matter, energy is created, and the relationship between that. That's just kind of some good information to know. We talked about the law of conservation of energy. Conservation means that it stays constant. So, and we're going to keep it, we're going to preserve it, we're going to maintain it. Now, in a pendulum, if you put this on, it's supposed to go back and forth and show that it's supposed to show the animation, but it doesn't work on the Google Slides, and it certainly doesn't work when I'm not in the slideshow format. But the way that it is that when the pendulum bob is raised up, like when we did the pendulum, before you let go of it, that's when it was at maximum potential energy and it wasn't moving. So it had no kinetic energy. When you let go and it starts to swing, as it gets down to the bottom, it has zero potential energy and it's all kinetic energy. And that kinetic energy carries it through. And as it raises up, because of gravity, it slows down. And as it raises its elevation up, it's gaining potential energy. And so then it goes to maximum potential energy. And then when it comes to a stop, just as it's swinging back and forth, as it comes to a stop again, it's at maximum potential, zero kinetic because it's not moving. And then it starts to move. And at the bottom, it goes to maximum kinetic, and then it goes back up to maximum potential. And in the law of conservation of energy, the pendulum would go on and on and on. Same thing with the law, Newton's laws of motion, that an object in motion would tend to stay in motion unless acted on by an outside force. And that outside force is friction. It's because of friction that the pendulum just doesn't keep spinning and spinning and spinning. So we look at systems, and systems could be a bicycle is a system. It could be a wind-up toy is a system. It could be a solar panel that we're using to produce light or using it for some other electrical production. All those things are systems. And within those systems, we're constantly converting from one form of energy to another form, from one form of stored energy or potential energy to a kinetic form of energy. And that kinetic form of energy is the energy that we are consuming. So typically the source of energy is typically potential energy. For example, if you have firewood, the wood energy is stored in the cells of that wood, and it is potential energy. But then we burn that for heat, we burn it for light, and heat and light is being given off, is in motion, and that is kinetic energy. A battery has chemical energy that is stored in it, that's potential energy, but then we use that battery to convert it into motion, say with a motor, say on a drone, that we get the spinning blades on the drone, that's kinetic energy. So we're taking the source of electrical energy and converting it into some usable mechanical form of energy. And so the stored energy is potential energy. The movable energy is kinetic energy. And so it's important to understand the relationship between potential and kinetic. But to go from potential to kinetic, or from kinetic to potential, or from potential to another potential source, or from one kinetic source to another kinetic source, some of the energy that's going to be converted is going to be used up because of friction, because heat is given off. Like when you rub your hands together and your hands feel warm, it produces heat. Some of that friction produces heat. And energy, the law of conservation of energy basically says that heat is accounted for that. And so when we looked at and we engineers take that into designing a system, whether that system be an engine inside of an automobile or anything else that uses and consumes energy, such as a light bulb or a radio or anything, a hairdryer, anything that we're using for energy consumption, we have to be concerned with how those energy conversions are. Is it safe to use? And is it the most efficient type of energy conversion that we have to be able to accomplish the job that we're using? And also it considers what is available forms of energy. So the sun is the primary source of energy for the earth. And solar energy from the sun is carried to the earth, and it can be directly converted directly into electricity through solar panels. But green plants also convert the sun's energy into starches or sugars, which is chemical energy. So we have the radiant energy from the sun, from the solar energy, from the light, that we can convert into electricity with solar panels, but we can also convert that into chemical energy through green plants doing photosynthesis. In an electric motor, we take electrical energy and turn that into motion, and then we convert that motion into whatever usable form of motion we want that to be. In a battery, chemical energy is stored, and when you can make it a complete circuit, the chemical reaction happens that produces the electrical energy, and then that electrical energy is used for whatever format that is desired. We can also take mechanical, when we refer to mechanical energy, we're referring to kinetic energy or energy of motion of something, right? When something, that's mechanical energy, when something is in motion. So when we have water that is falling, we consider that mechanical kinetic energy. There's also a mechanical potential, and that's when work is done to something. But mechanical energy is most commonly referred to as kinetic mechanical energy, and that's when something is moving. So if we can get something to move, that's considered to be mechanical kinetic energy, or just oftentimes mechanical energy for short. And so we can take mechanical energy from waterfall and convert that into electrical energy by using a generator. In a car engine, typically, I know we call them motors sometimes, but it's more appropriate to call electric motors, where we use electrical energy to get motion, or mechanical energy, a motor. And then in a car, automobile, or in a dirt bike, what have you, in a lawnmower, we call them an engine. And an engine is a combustible engine. What that means is it combusts, or it burns up the gasoline, which is the fuel. And then that fuel is the energy from the burning of the fuel is then converted into mechanical energy. So when we look at forms of energy, energy can exist in several different forms. The first one we'll talk about here is thermal or heat energy. This is the energy of an object due to its temperature. Remember all the kinetic theory of matter, that all matter, atoms and molecules, all particles, all matter is made up of atoms and particles, right? And those atoms and molecules are constantly in motion. And the faster they're in motion, the higher the temperature. The slower they're in motion, the lower the temperature. So the amount, and so heat energy involves, remember the scenario we talked about with what has more energy, a cup of hot chocolate versus an iceberg? And the answer was the iceberg, because it was so much more mass, so many more molecules. So when we talk about thermal or heat energy, it's about the temperature, but it's also related to the mass to figure out what the total amount of energy is. And that's a topic we studied way back in November. Light energy is energy available in the form of electromagnetic radiation. Electromagnetic radiation is radiation in the form of waves. Remember, we studied heat back in that thermal energy, and we said that heat can be transferred 3 different ways: through conduction, convection, and radiation. Radiation is in the form of waves, but it's electromagnetic waves, and And those waves do not need a medium to pass through, which is why energy from the sun passes through outer space, has nothing to pass through it. Radiant energy is the only energy we can get from the sun. We can't get conduction or convection because in those you need some kind of matter to transfer it, to move it. Electrical energy, we studied this in December. And then parts into January with electrical energy, with electricity. And it's energy transferred by electrical current through a circuit. Sound energy. I haven't talked much about sound energy, but sound energy is energy in the form of waves. It's a different type of wave. It's what we call a compression and rarefaction wave. So it compresses and moves apart. And so when a speaker moves in and out, what it's doing is it's vibrating the air, and then those vibrations in the air pass on to your ear, which causes your eardrum to vibrate. But sound is an energy, and it's a product that's given off. Kinetic mechanical, again, this is energy by a moving object, and this could be by a machine, say a bicycle that has moving parts. You see the picture there of the guy running, but oftentimes when we're converting it into usable forms of energy, we're using some type of simple or compound or very complex machine to be able to get the energy that we want. And our lives are completely changed by the machines that are around us. Chemical energy, you see the pictures of food. We get chemical energy by eating food, and that's our body's primary source of energy. In a battery, there's two main types of batteries, and that is ones that are one-time use, that they have products inside of them that have chemical energy that form a reaction that give off electricity as a product. Then we have the rechargeable ones. Remember my example earlier in the year of a rechargeable battery is more like a bucket. You fill it up with charge, and then you hook it to a circuit, and it drains, and then you fill it back up when you recharge it. So in this case, with chemical energy, we're talking about the type of the one-time use batteries, the 9 volts, the C cells, the D cells, the AAA, AA, the ones that you plug them in, and once they're dead, and you can't use them again because there's a chemical reaction that's stored in there to be used up. Nuclear energy, we have a nuclear energy power plant, an atomic power station in our district at Peach Bottom that harnesses nuclear energy, and we use that energy from nuclear energy to produce electricity. There's also other forms of nuclear energy that are used. Of course, the sun is powered through nuclear energy. And then we have potential energy, and you see the picture of the slingshot. Slingshot by itself, when it's not being held, it doesn't have potential energy. But when you pull back on the bands, when you pull back and you stretch it, you're doing elastic potential energy. And in the picture of the roller coaster, when the roller coaster is at the top of the track, because of its height, because of the work that's done to it to get it there, it has gravitational potential energy. So both gravitational and elastic potential energy are two different types of potential energy. The elastic potential energy, by the way, sometimes that's referred to as mechanical potential. Remember I said that there's mechanical kinetic or kinetic mechanical. You'll see them both ways, depending on which website you go to. But elastic potential is sometimes referred to as mechanical potential as well. Not quite often as much. And for all the things that I use in class, I always try to only use mechanical when it refers to kinetic. Simply because there's gravitational and elastic potential energy, and it's a little bit less confusing in that way. So when we're looking at energy transformations, we can look at a picture and we can say, okay, well, what types of energy transformations exist in this picture? And I will tell you that there's far more than what we're just showing you. But basically, we're showing cars moving down the road, right? So their primary source of energy is the gasoline that's in their tanks. And the gasoline that's in their tanks is used to produce heat, which is then used to produce mechanical energy to get it moving. But the cars use that gasoline to produce much more than just motion. You got the lights on the headlights, you got noise that's being produced. And so there's all kinds of energy transformations that we have there. Here we have a scenario where sunlight is shining on a solar panel and it's charging a battery. So that's chemical energy. But then, of course, that battery, you're going to hook that up. At this point in time, it's not shown, but there are other conversions that we have. A light bulb. The input is electrical, the output is light, but keep in mind it's also giving off thermal energy, it's giving off heat. It's part of the law of conservation of energy, because if we measured the amount of electrical energy that went into it and the amount of light energy that came off of it, they would not be the same. And the law of conservation of energy says that they have to be the same. So what accounts for the delta or the difference? And that difference is the amount of heat energy or thermal energy that's given off. So when we go to the store and we look at different light bulbs to purchase, there's a variety of different types of light bulbs. There's incandescent light bulbs, there's compact fluorescent light bulbs, and then there's LED light bulbs. Well, the incandescent bulb, it's the oldest technology, and as we get to the newer technology, it's more energy efficient. But the incandescent bulbs, where it has a little tungsten filament that glows, it produces more heat than it produces light. So it's not the most efficient light bulb. Then we have the compact fluorescents, which actually, instead of an actual filament, they have a little drop of mercury inside of that. When electricity passes through there, the mercury vaporizes and it gives off light. And so it produces far more light than the amount of heat that an incandescent bulb would do. So it operates at a much cooler temperature. Then we have the LED bulbs, and the LED bulbs are even better still. And so when you compare the different bulbs, if you were to go to the store, you're not going to get a 100-watt compact fluorescent or compact or LED bulb when it'll say it's comparable to a 100-watt incandescent bulb, or a 75-watt or a 60-watt or a 45-watt. We have the different wattages because obviously it takes energy to run these light bulbs, and so there's different types of task lighting. In your kitchen, where you're cutting with knives, you want it to be really, really bright. So you might use a 100-watt bulb. You might use 300-watt bulbs. Whereas in a closet, you might be able to get away with a little bit less light. It's not, you don't need quite as much light. Some people need a little bit more light to be able to match clothes, but nonetheless, you might be able to get away with less light. In a hallway, you just need enough for safety to be able to move back and forth. Perhaps you have a room where you have dimmer lights anyway because you're watching television or something like that in that particular room, and you don't need it to be really, really bright. So there's different types of task lighting, and so there's different wattages of bulbs based upon the need that you have. Because it relates to how bright it is and the mood that everybody wants, but also it relates to the amount of energy that you are consuming. If we just went for max light in every single usage, our electric bills would go sky high and it would be too expensive to do. So we want to match the amount of light that we need for the task that we're using so that we're not paying an exorbitant amount of energy in our bills. Well, anyway, when we look at incandescent bulbs versus compact fluorescents versus LEDs, they'll say they're equivalent to like a 100-watt or 75-watt or 60-watt or 45-watt bulb, but it uses much less, maybe 15 watts, maybe even 5 watts or 3 watts, because they're far more energy efficient, meaning that they take more of that electrical energy and produce more light and less heat to be able to produce the same amount of light. A tree, the incoming is light energy and it produces chemical energy. This is a motor, takes electrical energy and produces mechanical energy. In a hairdryer, we're using electrical energy. That's the input here. And it has two main products. It's got the heat, the thermal energy, and then it's got the fan to blow it. So we have two products there, and both of those products are intended. In a car, I went too far. In a car, we take chemical energy from the gasoline, and we use that chemical energy to produce electrical, sound, mechanical, light, thermal. There's all kinds of actions that we power with the gasoline that's in our cars. A radio takes input is electrical energy and it produces sound energy. There's also some light energy that's produced on the face of the radio, but the intended output there, at least for the main reason, is for the sound. In a fire, we have chemical energy from the wood stored in the wood, and then it gives off the thermal as well as the light energy. So it gives off light and heat energy. These are called Sankey diagrams, and it basically shows the input and then the useful output versus the wasted output. Now, in a real technical Sankey diagram, the width of the input measures the amount of energy that's going in, and the width of it measures the amount of energy that's coming out useful versus the amount of energy that comes out that's wasted. And this is basically looking at the efficiency of a particular device. Remember, I was talking to you just a moment ago about light bulbs, and the different types of light bulbs have different amounts of efficiency. Well, we use energy in all kinds of devices. Every time they upgrade and come out with a new smartphone, the newest version of each brand of phone, one of their challenges is to be able to get that screen to be brighter, but consume less energy. And they make it bigger and they make it brighter, but it consumes less energy. And if it consumes less energy, then the battery lasts longer. And so then they have a better product. The same thing is with computers and Chromebooks and different variations and versions that we have with that. Televisions, the same way. Televisions, if they consumed large amounts of energy, you go to the store and you see these huge TV screens that everybody wants to do now because we have high definition signals and things like that. But the signals make it so that it's viewable, but if they were huge consumers of electricity, it wouldn't be as beneficial to it. So they've made those televisions, they've made them more energy efficient over the years. Other things too, such as refrigerators. Refrigerators are far more energy efficient today than they were, 30 years ago or 70 years ago. To some extent, they've gotten bigger because they're more energy efficient, so we can store more food in them. As opposed to maybe in the 1950s, 1960s, much smaller refrigerators that were more common back then. But these energy flow diagrams, or Sankey diagrams, are used to describe a device that consumes electricity. So once again, we start here with the light bulb. Its input is electrical energy. Notice the arrows. The arrows pointing to the device is the input versus the output. And then the one that's going downwards is the wasted output, the friction that's being produced, the stuff that takes away from its efficiency. So a light bulb's input is electrical energy. Its intended or useful output is light energy, and heat is given off. Here we have a microphone. Sound energy goes into the microphone, and electrical energy comes out of the microphone. Now, understand that the microphone just simply captures your sound energy and puts it into a signal. There's another device that's going to then take that signal and then transfer that to a speaker that produces sound somewhere else. But the job of the microphone is just simply capture that sound energy and convert it into an electrical signal. Of course, there's heat that's given off, and so that's a device that we have. Car engine, again, we're just talking about the engine. Chemical energy goes in. Kinetic, the spinning of the engine, which converts it into turning it into the tires and doing everything else. Heat and sound energy, it's a lot of heat that's given off. And of course, the engines make noise. Some of the newer hybrid engines are much quieter. And the thing about them being a hybrid engine is that they're designed to be more energy efficient. So we use less gasoline or less chemical energy in order to go a certain amount of distance. And so if we can produce less sound, you might not think that that's a big deal, but obviously it's more efficient, so that helps you to produce better fuel mileage and thus consume less energy overall. And then a plant, even though a plant is not a synthetic device, which is something, a product that people produce, a plant is a natural device. It's still a device that consumes energy. Light energy goes in, chemical energy comes out. That's the plant parts, and plants do give off heat energy as well in that process. Even though light energy contains heat energy, it's still given off in that type of thing. So that is the energy transformations. We look at those several basic types of energy. And when we look at any type of device, again, it could be a bicycle, it could be a scooter, it could be a dirt bike, it could be a radio or a smartphone or a computer or any particular device that you're using, from a pool stick to a baseball bat, anything that we use where energy goes in and energy comes out and it's converted or changed into one form or another, we want to measure it based on its efficiency and evaluate it in those regards. And that is the energy transformation notes.